Okay, alright, so I want to look next to this whole block and cart thing. So here's a block and here's a cart. They are, I'm going to call the block B and the cart C. They are being pushed to the right by the applied force F. And what happens? So let's look at the block here. And I'm going to use the same coordinate system for both, which is going to be X, Y. Okay, so for the block, what forces act on the block? We've got this applied force, of course, the one coming from the left, pushing it to the right. We've got the block's weight, obviously, mass of the block times g. Okay, we've got the normal force acting on the block from the ground, so I'm going to call that NBG. We've got also a friction force associated with that, right? Because there's friction here. Okay, so I'm going to call that force of friction, BG. That's probably excessive, but whatever. And then my last force, which I'm having some trouble fitting in, is going to be a normal force from the cart. On the block from the cart. Okay. Oops, phone call. Hold on. Okay, that was my mother. So I had to just tell her I'll call back in a bit because my students are important to me. And why won't this stupid mouse cursor move? Okay, there we go. Okay, so anyway, these are the forces acting on the block. And so let's go ahead and put them together using this coordinate system that we drew up there, but I will draw it again, just making it uglier this time. Okay, and sum of forces is mass of the block times the acceleration of the block. Actually, both the block and the cart have the same acceleration, right? And they're going to be going this way, so we'll just do that. Okay, so in the x direction, we have that applied force F going to the right, minus the friction force exerted by the ground on the block, and then minus the normal force exerted by the cart on the block, okay, equals mass of the block times the block's acceleration. Okay, in the y direction, we have a normal force on the block from the ground, and then we have the weight of the block, okay, and that is going to be equal to MBAY, which is 0, okay. And this is, I guess technically I should write MBAX here and then say, well, I know it's accelerating only in the x direction, so this is just MB times A. Okay, so moving on down, let's see, I'll try to get the cart in red here. So, there we go, red. Okay, so now for the cart, which, why is this so unsensitive? All right, so the cart, no, I wanted red. Okay, there we go. Cart. Okay, the cart's simpler, okay? Because the cart we only have, all it's acting is, we got the normal force on the cart from the ground. We've got the mass of the cart times cart's gravity, of course. And we've got the normal force on the cart from the block, okay? So, sum of forces on the cart is mass of the cart times A. In the x direction, then, we have n of the cart, or n of the block on the cart, okay, is going to equal mass of the cart times acceleration of the cart in the x direction, which is going to be mass of the cart times A, of course, because that's the only acceleration there is. In the y direction, we got the normal on the cart from the ground, minus the mass of the cart times g, equals mass of the cart times acceleration y, which is 0. Okay, so that leaves us all set. What we need to do now is calculate or figure out what happens as far as the interactions between these go. So probably the easiest way to look at this is to take, let's see, I'm going to go to purple, my red plus blue color. We're going to take this x equation here for the block and this x equation for the cart here, and we're going to add them together. And this is going to accomplish two nice things. First of all, we know that the normal force the block exerts on the cart or the normal force the cart exerts on the block, and the normal force the block exerts on the cart are a Newton's third law pair, which means they are equal and opposite. So the opposite notes we've already got here, but their magnitudes are equal. So NBC equals NCB, okay, in magnitudes. So, sorry, that's a little ugly. I'm not sure why this tablet is trying to turn to crap, but I mean, I know my handwriting is not great ever, but it's even worse today than usual. I don't know. Maybe I'm just cramping up. Okay, so anyway, if we add these two together, these two will cancel out, okay? So then you can get applied force minus the friction force on the block from the ground, okay? And then this cancels, this goes away. So just these two forces, these are the only outside horizontal forces acting on the block cart system, okay? That's going to equal mass of the block plus mass of the cart times their acceleration, okay? All we have to do now is calculate this FFBG, right? That's the friction force the ground exerts on the block. And everything else, it's that pushing back that way on the block, and the applied force pushing to the right, and those are going to add up to the mass of the total system times its acceleration. So let's go now and find out what that friction force is, because that friction force is going to be, as you recall, mu k times the normal force, right? And so the normal force of the block on the ground, or the ground on the block, we can find here from this equation. So from this equation here, we can learn that the normal force on the block from the ground is just the opposite of the block's weight, okay, because those are the only vertical forces acting on the block. So, let's see. This means this friction force here of the block on the ground is going to be equal to mu k mass of the block times g, okay? So now, plugging that in down here, we can see that F minus mu k mass of the block g equals mass of the block plus mass of the cart times A. Okay? And so moving on down, the acceleration of these guys, final step here for the very beginning part, and come on, there we go. Acceleration equals applied force minus mu k mass of the block g over mass of the block plus mass of the cart. Okay, and that leaves us all done. So now, for part A, we want to show, well, so in the beginning we want to show, let's see, when they're both being pushed and accelerating for those first 2 seconds. Okay, so first 2.0 seconds, acceleration of the block and the acceleration of the cart are the same, and they're given by this, okay? And so we're going to plug in, and now I've got to go back and look at numbers. Force was 10 newtons, and mu k was 2.0, and each block was 1 kilogram. So let's see, this is going to be 10 newtons minus, I think friction coefficient was 0.2, not 2.0. What did I say? Did I say 2.0? I don't even remember now. Whatever. 0.2, okay, times the mass of the block, which was 1, times g, which I'm going to use 10 for because I just like doing that. And then mass of the block plus mass of the cart is 1 plus 1. So your acceleration initially is going to be 10 minus, so it's going to be minus 2. So 8 over 2 is going to be 4.0 meters per second squared. Okay? It has to happen for 2 seconds. So for the first 2 seconds, you're going to have this guy accelerating at 4 meters per second, both of them. So they're going to go like that, okay? Up to, after 2 seconds, they'll be going 8 meters per second. So I'm going to see if I can actually draw a line. Oh, yeah. Well, never let anyone tell you that Microsoft Paint isn't useful for something. Okay, so that is what happens with the first 2 seconds. Okay, now after that, what happens? Well, see, after that they're going to separate, right? So they accelerate, and then whoever is pushing the block stops. The cart is going to just keep going, right? The cart's got nothing to slow it down. This normal force isn't going to pull on the cart. So after they lose contact, the cart See, after they lose contact, this force is going to go away, and the cart is going to have vertical forces on it. So the cart will, assuming there truly is no friction, the cart will just sail off into the sunset, right? So the cart, I'm going to do the cart in red, and just do that. And I know it's a little off, but pretend it's a straight line. Okay. So the cart does that. Bye-bye cart. Okay. So this is the cart. Let's see, cart. That's better. Okay. Now the block. What does the block do? Well, the block. If we look at the block here, we no longer have this thing, this NBC here, right? That's gone now. Okay. So what happens now is that goes away, and that means, and so of course the applied force is also gone. So now the block only has, so this force is gone, and this force is gone. So now the block only has the MBG, and friction force. So the normal force for the block, this is all still going to be accurate, but the acceleration of the block, if you punch through the equations, and I encourage you to, but the acceleration of the block, so that's the first 2.0 seconds. After 2.0 seconds, okay, acceleration of the block should be negative mu k times g, which is going to equal negative 0.2 times 10, which is going to equal negative 2.0 meters per second squared. Okay, so then the question is, how long does it take the block to stop? If it's going to accelerate negative 2 meters per second squared, it starts at 8, right? So, I mean, you could plug in an equation, or you could just say, look, 8, and then after 2 seconds, or after 1 second, it'll be 2 lower. After another second, it'll be another 2 lower. Okay, and so then take and draw a line like this, and that's what your block ends up with. Okay, so that's how your block goes. Okay, and then so